Today we shall study about refraction at a spherical surfaces and mi- and lenses. We first consider refraction by a single spherical surface and follow it by thin lens. A thin lens is a transparent optical medium bounded by two surfaces. At least one of each should be spherical. Applying the formula for image formation by single spherical surface successively at the two surfaces of a lens, we shall obtain the lens maker's formula and then the lens formula, as shown in the figure 1. Now the refraction at a spherical surface. Figure 1 shows the geometry of formation of image 1 of an object 2 on the principal axis of a spherical surface at center of curvature C and radius of curvature R. The rays are incident from a medium of refractive index N1 to another of refractive index N2. We take the aperture or the lateral size of the surface to be small compared to other distances inward so that a small angle approximation can be made. In particular, NM will be taken to be nearly equal to the length of the perpendicular from the point and on the principal axis. We have for small angles 10 NOM बराबर MN बटा OM, 10 NCM बराबर MN बटा MC, 10 NIM बराबर MN बटा MI. Now for through NOC, I is the exterior angle, therefore I बराबर NOM plus NCM. I बराबर MN बटा OM plus MN बटा MC. Similarly, I बराबर कौन NCM minus कौन NIM. It means R बराबर MN बटा MC minus MN बटा MI. By Snell's law, N1 sin I बराबर N2 sin R. For small angles, N1I बराबर N1R. Substituting 1 and I and R from equation 1 and 2, we get N1 बटा OM plus N2 बटा MI बराबर N2 minus N1 बटा MC. Here OM1, here OM, MI and MC represent magnitudes of distances. Applying the Cartesian sign convention, OM बराबर minus U, OM बराबर minus U, MI बराबर B and MC बराबर R. Putting the value, we get N2 by B minus N1 by U बराबर N2 minus N1 by R. Equation 3 gives us a relation between object and image distances in terms of refractive index of the medium and the radius of curvature of the curved spherical surface. It holds for any curved spherical surface. Now refraction by lens. Figure 1a shows the geometry of image formation by double curvature convex lens. The image formation can be seen in terms of two steps. The first refracting surface forms the image I1 of the object 2. The image I1 acts as a vertical object for the second surface that forms the image at I. Applying to the first interface ABC, we get N1 by OB plus N2 बटा B I1 बराबर N2 minus N1 बटा B C1. Similarly, for the second interface ADC, we get minus N2 बटा D I1 plus N1 बटा D I बराबर N2 minus N1 बटा DC. For a thin lens, B I1 बराबर D I1. Adding equation 1 and 2, we get N1 बटा OB plus N1 बटा D I बराबर N2 minus N1 into 1 बटा VC1 plus 1 by DC2. Suppose the object is at infinity, it means OB tending to infinity and di barabar f. Equation third gives n1 vata f barabar n2 minus n1 into 1 vata bc1 plus 1 by dc2. The point where image of an object placed at infinity is formed is called the focus f of the lens, and the distance f gives the focal length. A lens has two foci, f and f dash, on either side of it, as the figure sign convention, bc1 barabar r1, bc2 barabar minus r2. So equation 4 can be written as 1 by f barabar n2 1 minus 1 into 1 by r1 minus 1 by r2. n2 1 barabar n2 bata n1. It is called lens maker formula. Now, that is, usual is full to design lenses of desired focal length using surfaces of suitable radii of curvature. Note that the formula is true for a concave lens also. In that case, R1 is negative, R2 is positive, and F is negative. So by equation third and fourth, we get n1 by OV plus n1 by di or n1 by f. Again, in the thin lens approximation, B and D are both close to the optional center of the lens. Applying the sign convention B over minus U di over V, we get 1 by V minus 1 by U over 1 by F, called thin lens formula. Magnification, it is denoted by M. Produced by a lens is defined like that for a mirror as the ratio of the size of the image to that of the object. For lens M barabar h dash by h barabar v by u. When we apply the sign convention, we see that for erect and virtual image formed by a convex or concave lens, M is positive, while for an inverted and real image, M is negative. Power of lens. Power of lens is a measure of the convergence or divergence which a lens introduces inside falling on it. Clearly, a lens of the shorter focal length bends the incident light more while conveying it in case of a convex lens and diverging it in case of a concave lens. The power P of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optical center. Tan theta barabar h bata f. If h barabar 1, tan delta barabar h by f. If h barabar 1, tan delta barabar 1 by f, or delta barabar 1 by f for small value of delta. Then P barabar 1 by f, the SI unit of power of a lens is diopter, D. 1 diopter barabar 1 meter inverse. The power of a lens of focal length of 1 meter is 1 diopter. Power of lens is positive for converging lens and negative for diverging.